The scientists and the craftsmen work side by side, continually developing new ways of making electricity work for the benefit of man. British skill and British craftsmanship have long held an honoured place throughout the world, and British goods are constantly finding their way into the farthest corners of the earth, doing their bit to help the national economy and to bring benefit to those who use them. One of the greatest manufacturing concerns of its kind in Great Britain is the English Electric Company, with its headquarters at Stafford. Thousands of workers are employed in the vast workshops every day. And so they are at its other factories, at Rugby. Bradford, Preston, and Liverpool. Here in Stafford is under construction electrical equipment that will eventually find its way not only throughout Great Britain and the widespread lands of the Commonwealth and Empire, but into every corner of the world where people have come to know that the slogan "Made in Britain" means superlatively well made and designed. This vast erecting shop, extensive though it is but a small part of one of the works where the company manufactures products of the highest technical standards. Here are giant transformers under construction, destined for the world's power systems. In a neighbouring shop, the associated switches to control the power are made. Here are the generators, both for the steam power stations and those used to harness some of the world's water power for the much-needed reinforcement of power supplies both at home and overseas. The whole of this experience, research and manufacturing organisation is at the service of all who need the company's products, not least the railway engineer. The English Electric Company were pioneers in the field of using electricity as a source of power for railway traction. For the first electrified main line in Great Britain, between Liverpool and Southport, was powered by Dick Kerr and Company, one of the four firms which amalgamated in 1919 to form English Electric. It was at Preston that some of the very earliest electric traction equipment was designed and made. As far back as 1898, in the days of London's earliest tube railways, these works were producing the electrical plant to drive the train. And as well as this great pioneer development, some of the very earliest tramways in the world, another phase of electric traction, were being designed and manufactured here. This great erecting shop has seen the birth of each development as it's come along. Larger and faster and more powerful electric locomotives to the electrified railways which, during the last 50 years, have come into being all over the world. Japan, India, Ceylon, New Zealand, Canada, Poland, Denmark, Brazil. There's scarcely a corner of the globe that hasn't utilized electric traction equipment from these works. driving power that makes an electric train travel along the rails, the heart of the locomotive, is the motor. Here, large motors start their complicated travels through the maze of workshops. The cast steel carcasses are being machined. Machine tools like these have been specially designed for the purpose. The armature is the part that goes round, the part that drives the wheels. The utmost care must be taken in its manufacture. These coils, which carry the current, are first formed and then go through many stages of insulation and patient assembly and checking before the armature is complete and the commutator is added. Diamond cutters are used to get the finest possible finish, and the whole perfectly balanced on machines specially constructed for that purpose. Another traction motor nears completion, one of the many hundreds that will power new and extended systems at home and abroad to make the benefits of quick, clean travel available for more and more millions of passengers and tons of freight each year. Whether they be motors for the 3,000 horsepower locomotives of Brazil, motors for the Empire, motors for the British Railways, or motors for trolley buses, they all represent the most modern design and manufacturing ability. The successful operation of any electric locomotive depends largely on the efficiency of the control gear. Scores of detailed parts go to the making of a single contactor, and as well as contactors, there are compressors, controllers, gauges, meters, instruments, all calling for the highest degree of skill, both in design and manufacture. The result, here it is, a complete control equipment for the electric motor coaches for New Zealand. One man operating a small handle has to control enormous currents by means of this equipment, all of which has to be fitted underneath the coach and yet be available for maintenance whenever required. The framework of electric locomotives and motor coaches begins to take shape in this part of the works. For long life and reliable service, as well as for comfort for those who ride in them, the bodywork be given as much care in design as all the other details in this assembly line. English electric designed locomotives are made by subcontract elsewhere. This is the first of 15 3,000-volt, 3,000 horsepower locomotives for Brazil, the largest and most powerful yet made in Britain. When the time came for the application of the diesel engine to rail traction, once again it was this company who were pioneers in designing and constructing diesel-electric locomotives for the railways of Great Britain. Since that time, English Electric has sent an ever-increasing number of diesel-electric and electric locomotives abroad, where they've continued to win for themselves a reputation for efficiency, reliability, and an unfailing ability to do the work for which they were designed. In 1947, number 10,000, the first express diesel locomotive for Great Britain, was produced. This was achieved by the combined resources of the English Electric Company and what was then the LMS Railway Company. This first diesel locomotive is powered by a 1,600 horsepower engine, which, together with the whole of the control equipment, was designed by the English Electric Company at its various works. While it was under test engineers lived with the giant 16-cylinder, 1,600 horsepower engine day and night for over a week. Delicate instruments and meters were used to check over every part of her, and the readings taken at frequent intervals provided a perfect case history of the job. The diesel engine and main and auxiliary generators form one unit. It was specially designed and developed for rail traction, and the governing and control gear is arranged for complete remote control. Incidentally, this 17-ton engine is the largest V-type to be built in Britain. The engine was taken to the LMS works at Derby. Here, a new workshop is the first to be established in Britain exclusively for the construction and maintenance of diesel and diesel-electric locomotives. The decision to construct number 10,000 followed the successful experience gained by the LMS over several years of the application of the diesel-electric principle to shunting locomotives. By the use of these shunting units, of which over 100 are in service and more on order, increased availability and saving in operating costs have been obtained. Now the application of the principle has been extended to mainline passenger and freight services. The first main stage in the construction was dropping the engine into the frames. Everything connected with the assembly of this unit was new, so that at every stage new problems had to be faced and overcome. Slowly, carefully, the engine is lowered into position. The brains of the locomotive are mounted in a dust-tight frame. This control equipment consists of electromagnetic and electro-pneumatic contactors, relays and reverser, and is operated by master controllers to be found at each end of the locomotive. Bulkheads are fitted at each end of the locomotive behind the driving compartments. With the fitting of the side plates, number 10,000 is beginning to look like the finished job. The body, sides and roof, together with the nose ends, form one assembly which is supported on two pivots placed at each bulkhead behind the driving compartments. The frame is thus free to deflect without stressing any of the superstructure. The last section of the roof, that over the fuel tanks, is being fitted into position. There are hinged doors in the roof so that the diesel engine covers, pistons and other parts can be easily removed for examination. The inside of the body, including the driver's compartments and the roof, are sprayed with asbestos to reduce noise and to provide good insulation. Power from the main generator is transmitted to 6 traction motors, 3 on each of the 2 bogies. Adjustable cushioned seats make driving number 10,000 almost an armchair job. A cab is provided at each end. Fittings include the main controller, brake valve, windscreen wipers, sanding and hooter valves. There are defrosters and sun blinds. Dashboards with indirect lighting to the instruments give the crew information on the working of the engine and equipment. Almost the last job before number 10,000 can take the road is to provide her with wheels. The 2 bogies, each with their 3 traction motors, are pushed under the frames and superstructure. These bogies, of entirely novel design, are fitted with roller-bearing axle boxes. Painted black and chromium, locomotive number 10,000 is an impressive sight as she moves slowly out of the shop for the first time. The men who for weeks have worked at her building are there to give her a send-off. After short preliminary trials, diesel-electric locomotive number 10,000 was run from Derby to London. The railwaymen, who all their lives had been used to the familiar tattoo of the exhaust of steam engines, stopped a while from their work as the black and silver softly purring diesel streaked by. Is this, they thought, the shape of things to come? Romance still clings to the steam engine, but romance alone will not run the railways. New ideas, new methods must be given a chance to succeed. At Euston, on the 17th of December 1947, the new locomotive made its first public appearance. And so, with the entry into the railway service of locomotive number 10,000, a new page has been turned in the history of rail development in Britain. While the steam engine must remain for some considerable time the principal means of locomotion, it now has, in number 10,000, a new challenger. Since her trials, number 10,000 has operated on the arduous route between London and Derby, passing Luton, Bedford, Leicester, Loughborough. She's done 2 round trips a day, with a total of 512 miles, and the train hauled has varied from 9 to 12 coaches. Nowhere was she called on for her maximum effort, but speeds of well over 80 miles an hour can be attained.
In 1955, the British Transport Commission announced a 15-year plan for the modernization of British railways. Vast and imaginative in scope, it heralded a new era of travel for Britain and presented an exciting challenge to British railways and the locomotive manufacturers. A feature of the plan is electrification of certain main and suburban lines using high-voltage AC power. For example, trunk routes between Liverpool, Manchester and London, and the North East and London, will take power from the countrywide national grid system, passing it to the locomotives through an overhead contact wire supported by the lightweight structures which the high voltage system permits. Another feature is the introduction of diesel traction on the remaining routes. Of the 2,500 diesel locomotives called for, many are already in service, different types for different purposes. The 2,000 horsepower diesel electric for express journeys from London to the north. The 800 horsepower diesel electric for heavy freight. The 1,200 horsepower diesel, here operated in multiple with one driving crew. The 1,250 horsepower diesel electric designed for mixed traffic. The 2,000 horsepower diesel hydraulic for express services to the southwest. To obtain immediate economies, diesels are already being used on routes that will ultimately be served by electric trains. For the passenger feeder lines to the trunk routes and where suburban electrification is not warranted, diesel multiple unit trains have been selected. Suburban and cross-country services are seeing more and more of these new diesels. Light, comfortable and fast, they are proving very popular. The new generation of train spotters is growing up with diesel and electric trains. During their lifetime, a changeover will take place as revolutionary as that from horse to steam, an evolution from steam to electric and diesel power.
The M1. At just 74 miles, it was the first long-distance motorway in Britain. It stretched from St Albans in Hertfordshire to Dunchurch in Warwickshire. The M1 was opened on the 2nd of November 1959 by Ernest Marples, the Transport Minister for Macmillan's Tory government.
It is in keeping with the bold, exciting and scientific age in which we live.
It's interesting, the first real motorway in Britain, the M1, which opened in November 1959, was basically a straight line. I mean, it's like a long concrete strip, just cutting its way through the landscape, paying virtually no reference to topography. I mean, who cares about hills, rivers, vales, valleys? Just build as straight as you can. That was how motorways were conceived. Straight line, very fast, no messing around. And I suppose, as a reflection of that, the actual design, the engineering, and the minimalist architecture around it in terms of structures, bridges principally, were just brutally functional.
Highly efficient organisation on a vast scale, both played a vital part.
The building of the 55-mile northbound section was split into 4 contracts.
The £16 million contract...
John Lang & Sons Limited secured them all, but had just 19 months to complete them.
Headquarters at Newport Pagnell.
The consulting engineers were Sir Owen Williams and Partners. Sir Owen had been knighted for his design of the original Wembley Stadium and was a well-known public figure.
Sir Owen, this is something almost revolutionary in this country in the way of road construction, isn't it?
I think I can say that there is no other greater effort being made in the world comparable to this.
Well, Sir Owen was a very forceful character. He was a great man to work with because he was in a wonderful fund of anecdotes because of all the people he'd met during his career. But he'd established this reputation as a very prominent engineer-architect.
48 surveyors and engineers were engaged in calculating and setting out the centre line of the motorway.
I forget now how many people there were, landowners and people who were involved in that, but there must have been about 300 odd. And he went to see them all, personally, so that, you know, the objections to the road, the objections to the road were minimal because he'd been to see people, and of course at the time building a motorway and trying to come to terms with the sort of new motorway age was something that people were all in favour of. I thought it was great.
To prepare an accurate construction program...
In all, only 5 houses and 3 bungalows were demolished to make way for the M1. $20 million tons of rock, chalk and earth had to be excavated to clear the land. The site was so vast that the latest technology was used to survey it.
Keeping track of what's happening can best be done from the air. By helicopter, checks can be made all along the route in a matter of hours.
5,000 men were employed to work on the project, and mobile canteens were built every 2.5 miles to cater for them. In all, 183 bridges were built on the M1. On average, one was completed every 3 days.
The scene, I mean, you've got to imagine the scene. It's hard to believe that great construction programme. I mean, it's heroic in scale, Roman in scale, Victorian in scale. The M1 was built at a rate of 1 mile every 8 days. I mean, today, when we find it very difficult to build an Olympics or to build a Wembley Stadium, try and imagine what that means. Just really think, 1 mile every 8 days, completed. It's really, really fast. It's the speed the Chinese work today in rebuilding Shanghai or Beijing. That's what the Brits could do at the time.
Cuttings, embankments, bridges, two-level junctions, all were taking shape in the scarred earth.
I could name and remember very clearly, particular, I suppose, the muck shifting foreman or the actual agent, the sub-agent on muck shifting, because these were characters of their own. They hired and bought in enormous fleets of often great big motor scrapers, things capable of carrying 40 metres of muck at one particular time from one place to another. These guys had a life and a way, you know, and a rule that nobody got in their way because these machines were enormous.
One machine doing the work of up to 1,000 men, and each one costing about as much as a pick and shovel man might earn in a long working lifetime. So the earth-moving navvy of today is first and foremost a machine man, a driver. A driver as skilled in his way as the driver of a track racing car.
And had these big outlets like cleaning the rest of the ground to get it level, you know, and so just like a sand dune, these big machines flying up and down.
How long did it take you to get to know how this machine reacts to all these controls?
Well, I'm quite a while now working at machineries for Wimpy's. I'm 7 years driving this type of machine.
Men of all colours and creeds from all over the Commonwealth are helping to build this great new motorway.
The construction of the M1 was really, I suppose, a 1950s version of the building of the railways 120 years before. The men that built them were essentially navvies.
I've navied here in Scotland, I've navied in the south.
The term navvy is derived from the inland navigators, who built the canal system in Britain in the 18th century. Mostly Irishmen, navvy became the term used to describe all manual labourers. Between 1951 and 1961, over 500,000 Irishmen came to Britain to work in the building and construction industry.
A bold navvy man, me boys, a bold navvy man. I've done me graft and stuck it like a bold navvy man.
Planning for the Stafford Bypass commenced in 1957. A project long overdue to relieve the traffic congestion in the town centre. Construction started in June 1960. The 5¼ miles from Dunstan to Creswell section of the M6 Motorway took 2 years to build, costing £5 million.
Our office was in the loft over the old weights and measures department at the top of North Walls, which wasn't very good, but it was a big room where we could have a table which was about 14, 15 foot square to lay everything out. And as soon as the 25-inch plan was made in sections, then it was possible to start the 1/500 surveys for the bridge sites. Because I was the junior engineer principally concerned with wandering around across the countryside interviewing everybody as we went. And there were hundreds of landowners and people concerned, And from memory, and it's a long time ago, there were only 2 people who didn't really want us. Well, of course, it was necessary to cut a way through all the hedges and trees and whatnot to get the line through while it was being measured with steel tapes. We used 300-foot steel tapes, and of course you had to correct for temperature and elevation and everything in the normal way. And if any trees were in the way, well, they were felled, because we had a tree felling contractor following us up. But there was no opposition from the community at all. We were welcomed all the way through. Well, in order to set out the final centre line of the motorway, first of all you located the intersection points of all the straights on the ground by measurement from features. It might take 10 or a dozen measurements to get a good approximation to where you ought to be. And then, because of the undulating nature of the ground, you couldn't see from one point to the other, so we had towers constructed, portable towers in tubular steel, which we erected over intersection points, 3 or 4 miles away in some cases, so that the line could be viewed through with a theodolite.
A major problem facing the engineers was the crossing of the valley of the River Sow at Creswell.
A decision was made to go ahead with Creswell Viaduct before the rest of the motorway, and at that stage we hadn't designed Creswell Viaduct, and it was done in a frantic rush. There were normally, at that time, one engineer designed a bridge complete. There wasn't time for this at Creswell Viaduct, and so therefore one man was given the job of designing the abutments and the piers. Another one did the wing walls, and I did the deck. The deck, at least, had been designed so that the beams could be cast elsewhere. They decided to cast the beams on site. This was done on a portion of the site fairly close to the Eccleshall Road. Had hoppers for the stone and the sand and the cement, and they mixed the concrete on site and made the beams. After they'd cast the beams, they then had a little railway track. But the locomotive was used to pull the beams more or less into place, not quite, to pull them onto the correct span, because as you'll realise, the site was getting on for half a mile long, I should think. Then they pulled it along the railway track to the span, and then jacked it up or down a bit, I'm not quite sure, and then moved it along sideways on rollers to where the bridge beam had actually got to be. We did enjoy the work. It was, because it was, I won't say it was in the forefront of design work, but the number of jobs that had been done with pre-stressed concrete was not terribly great. There were no codes of practice. After we'd finished all the design work, the County Council sent us on a design course to the Cement and Concrete Association. And we were very pleased to see that we didn't have to make any alterations. Unless we'd thought, it looked fine if we have to start all over again. But luckily, we'd done things right.
The bypass was opened on August the 2nd, 1962, by Ernest Marples, Minister of Transport, it being the first section of the Birmingham to Preston motorway to be completed.
I'd seen in the local newspaper that the Stafford Bypass was to be opened by the Minister of Transport at this certain time on a certain day, and having that the sort of job where I was a bit flexible, I took an hour or so off and went in my car, parked it at the Dunstan Island, walked up the northbound access road and joined the throng at the top, which was only a small one, and I was surprised not to be asked for identification or something of this sort, but nobody took any notice of me, probably because the camera I had at the time was the sort used by pressmen. I was able to get just this nice picture of Ernest Marple's cutting the ribbon, and there it was, the M6 past Stafford was open.
Within weeks of the motorway opening, some 8,000 vehicles daily were recorded, over half being heavy goods vehicles, relieving very considerably the congestion of the A34 through Stafford.
One of the great treasures about Stafford is that it still sort of retains its original walled feeling. It has north walls, it has south walls, it has a jail gate, and here we are on Green Gate. We're now standing on the banks of the River Sound. Of course, the Sow's the main river that flows through Stafford. This area at the bridge on Greengate Street was where the brine bath stood. A blessed memory to all of us who learnt to swim with our flippers here. But the interesting thing is that they were brine baths. They were fairly antiquated by the time they were knocked down, but they were brine, and that is, of course, salt, and that's what Stafford was built on. Stafford was built on salt until such time as the salt extractions collapsed, and most of the north end of Stafford fell into the hole, really. And they had to stop, so the industry went. The other thing about along here where we're standing is that this is where there would have been wharfs for a canal. There was a canal that came from the Trent and Mersey across from St Thomas's Mill and into the town. You can still walk it, you can still follow the route of it, and there is quite an active campaign on at the moment to try and bring it back, and we could have canal boats in the centre of Stafford. But as a building, it had this wonderful tower. You always took your time by the brine bath tower. And so when they replaced it, they at least kept a tower. I don't know quite whether it's architecturally as interesting as the previous one, but it was a very strange building. It had this awful smell of verrucas, as you might say. You know, it was a very, very dubious place, the old brine bath. So maybe things move on, but maybe they don't. But it's a shame that we're not still seeing canal boats in the middle of Stafford.
Salt production has developed from the evaporation of brine in open pans to today's highly automated vacuum plants. Stafford, though always a junior partner to the larger Cheshire firms, did, in its most productive years, produce about 8% of the country's output, from both open pan and vacuum plants. Salt was sent away as far as London and East Anglia, and there was a thriving export trade, particularly to Nigeria. In the 50s, Stafford had 3 works on the common, served by the Stafford to Uttoxeter railway line. In all, there were buildings housing some 30 pans, a vacuum works, and several pump houses. At Basage, there was a vacuum plant on one side of Basage Lane, and a soda crystal works on the other side, all tapping the vast supplies of brine under Stafford. Today, it is quite incredible how little traces of this once major industry remain. There are pieces of abandoned pipework to be seen in the water meadows near the Basage works, possible remnants of the distribution network that once connected the pumps on the common to Basage and the brine baths. No traces of the Basage railway sidings remain. An industrial estate has obliterated the old works, and the vacuum plant is now a residential caravan park. Astonfield's estate has covered all the sites of the common works, but the old Weybridge office remains, and a social club, the name and abbreviation of Amalgamated Salt. There are scanty remains of the common railway station and the once busy railway sidings that served the works. But of the works themselves, nothing remains.
And the copper strip and the
The County Museum has done its best to preserve some artefacts, but much of the history is held in the memories of those who worked in the plants and those who lived near them.
Years and years ago, they were searching to find a source of water. They intended to build a series of water pumping stations, and instead they found brine. Hence, they built the salt works around it, sort of thing,
The Borough Waterworks engineers found brine at 360 feet in 1877. It took some years before this expensive mistake could be turned to profit. A pump was installed, probably like this beam pump, to pump brine to a works on the common near the Stafford to Uttoxeter Railway. The Stafford Salt and Alkali Works opened in 1893. The public baths and brine baths were built on Bridge Street in 1892. They needed an assured supply of brine, and the new Stafford Salt and Alkali Works was contracted to supply the brine from their pump. After a visit by the Duchess of Teck in 1895, the baths became known as the Royal Brine Baths. In 1894, a new works was built in Basage by Stafford Salt and Alkali to exploit the transport opportunities provided by the Staffordshire and Worcestershire Canal. This new works was fed with brine by a pipeline from the brine baths along the River Sow. By 1900, there were 3 works on the common, and this continued until the late 50s. ICI's Tillington Works, the old Chance and Hunt Works, was further up Common Road, behind the Weybridge, on the site of the council waste disposal site. This film was shot in 1959, just before closure. The pan we can see is producing common salt, which was destined at the time for gritting the roads in winter.
The railway lines used to be down here, and there used to be the LNER station there, and they used to shunt all the trucks down here. And then my grandfather used to have a team of horses, 3 horses, and used to pull all these trucks up to the bays wherever they wanted to load them.
And then eventually, when the war came along, they replaced these big draft horses with a tractor sort of thing, didn't they?
Despite competition from vacuum salt, the centuries-old open pan method had the virtue of simplicity and of being able to produce easily a range of grades of salt, from fine to very coarse. The longest-running open pans in Stafford were those of the former Stafford Salt and Alkali Company, and although they were gradually run down in the 60s, they survived almost to the end of salt making in 1970.
Most of the buildings were wooden constructed with corrugated asbestos roofing with a big gap at the top to allow the steam to come out. We couldn't use, metal ironwork just corroded, so it was mainly, they were mainly built of timber, about 12 inches square. And Henry Venables used to supply us with most of the timber.
And I came down and I thought, this place is derelict. And it did look derelict, but it wasn't. That was the way it had to work. With salt, there was no way you could keep things square and nice. It was so corrosive. As it wore down, sometimes it was better when it was worn out than when it was new. It was just an old way of making salt, that we'd superseded by having a vacuum plant system, you see.
The works on the common produced 3 types of open pan salt. Bars of salt formed in wooden tubs and called lump salt, sold whole or cut into smaller blocks, or ground and bagged, and loose common salt and fishery salt. Further processing gave other types of salt.
If you can imagine like a tank about 18 inch or 2 feet deep, and they were filled with brine, then underneath each pan, in the early days they had what they call open fires. They were real big fires. You could throw 2 or 3 ton of coal on each one, sort of thing. And generally speaking, the finer the salt, the hotter you got the pan. The block process work, they literally boiled, didn't they?
Yeah. If you were sort of a layman, it was just a big tank, but it wasn't. When you make a pan, you actually make the sides with about a 10-degree angle on them. And this follows all the way around the pan. That was mainly so that the people could get their toes underneath it and they weren't falling in. There was an handrail above their head that if they did actually fall, they could catch the handrail, which was just a piece of basically 4x4 as an handrail. The pan is actually concaved in the middle, so when the salt's made, It'll be made on the hot side of the front side of the pan, which is fired, and moved to the cold side of the pan. Then the crystals fall to the bottom, and then after they've accumulated enough salt crystals in the pan, then they're raked to the side, and then ladled out onto the hurdles, and then dried out and taken into the warehouse as salt.
The various production processes associated with lump salt required a more complicated layout. Attached to the pan house was a 2-storey hothouse for drying, cutting, grinding and packing.
The fires heated the pan at the front. Then the heat went down the pan in an action like sort of a snake action that went down past the stack, into the dryer, into the outhouse, back again, and then up the stack. And they used the heat to actually heat the pan, and then to go back into the hothouse to heat the hothouse before it actually went up the chimneys.
It would take about 8 hours to get the pans to boiling point and the salt ready for collection.
That's your empty tub sitting on the dogs. Okay, so you just went a little bit back. This is your pan, and that was the action. You fill your salt and you sort of ladling action, about 2.5 of these usually. You just give it a knock to fill it, and that was it. When they were full, you lifted them down off the dogs and put them on the hurdle to drain, and they'd perhaps be there half an hour or slightly more. This is what they call a lump man's barrow, and it was used when the lumps were tipped out of the tubs. This was used to take them in to the hothouse where they dried. So you picked them up, you put them on the barrow, squared them off, give it a rock, and lift your tub clean. Then you get your hopper, go around all the 4 sides first, and then square the top off, and generally fake them up so as they were nice and clear. When you'd got 10 on, you took them into the hothouse and put them in what they call the ditch to drain. They'd be there for a couple of days. Then you came to the men called lofters. They were the men who worked in the hothouse. Their job was to really dry them off properly, lift them out of the ditch onto the flue. They stacked them on the flues, and they were there for 2 or 3 days. They had to stack them with a slight space between each one so as the heat would get all round. But when they were finally ready for either wrapping or loading into wagons, the lofter used one of these. This is called a lofter's barrow, and he placed them on. You'd probably get about 4, and then 3, 2, 1 sort of thing, pyramid shaped. And then they were either sent out how they were. If they were cutters, they were put through a group saw and sawn into little blocks about the size of a house brick, and in turn they were wrapped in paper. But if they were 80s for export, they were left as a block, and they were wrapped in very strong waxed greaseproof paper, wrapped up and sealed with tape and sent off. That was it.
It was hard work all round in the salt works, but the making of lump salt was particularly arduous.
Lumpering was one of the hardest jobs you could have. Working in the steam all day just drained the energy down. You were constantly wet, and it was just an energy absorbing job. So you went on it because it was very, very well paid at the time. At the time it was exceptionally well paid, but you had to be tough to do it.
Ground subsidence was the problem. Uncontrolled brine pumping could lead to large-scale collapse of the land above. And this happened in Stafford. The effects of subsidence are clearly visible today in the plumber's shop outside Lotus and in Crooked Bridge Road. Subsidence caused Lotus major problems. The court had ruled, and 1970 saw the end of salt production in Stafford. The last of the close-knit, family-style companies that had employed generations of Staffordians would have no more workers' outings and no more characters like Lily.
Oh, we had some fun. It was one laugh when you went to work. The fun we had, you know. We were always laughing and having a bit of fun between ourselves. It was great. It was great. Hard work, but it was great.